Hey everybody, sorry about the delay there. If you did not already, please tell me what is your favorite podcast for the attendance today. I will be paying attention to your suggestions for my own personal gain. Midterms have been graded and grades have been posted, and you should have received an email from me with a document describing what was correct or incorrect on your exam. So please check that out. Make sure you agree with me. I encourage you to disagree with me, and we can discuss your answers if you want to. But definitely go back and figure out what you did wrong, as that is going to be very important in the future on the final and in senior seminar and in your life as a scientist beyond. Especially the determining uncertainties, stating uncertainties, propagating uncertainties. It's really easy to make mistakes with those. So go back and check what you did. Also, I emailed you. There's no class meeting on Thursday this week. I will post a digital lecture. It'll actually be 2 times worth. So 100 minutes, because I owe you one from last time too. So that will be all about binomial and Poisson distributions. Okay, questions, anybody? Alrighty. Then we need to talk about correlation and covariance. So let us look at this. Check these plots out. Oops. Looking at these plots, just look at the top for now, like right here, the one I'm circling. Let's say you took a bunch of measurements of X values, corresponding Y values, and plotted them, and it looked like this. Can you tell if X and Y are dependent on each other or not from that plot? It's definitely hard to tell for me. Looks like they're not, but maybe they are. Same thing for this one. I can't really tell if X and Y have any dependence on each other. Maybe, but I'm not really sure. But if I look down here at the bottom, let's say I take a whole bunch of data points again, I take a bunch of X values and corresponding Y values and plot them, it looks more to me now that X and Y are dependent on each other. Like as we increase X, it looks like we would also increase Y, or Y would correspondingly increase for this plot that I'm circling down here. So sometimes you can tell, and it's real obvious, like here, those points look really linear. That looks like a very straightforward linear dependence. But sometimes you can't really tell, like with this plot that I'm circling or this one. So it's nice to be able to quantify that. Are those things dependent on each other or not? Well, we can quantify how dependent they are on each other. And then we can answer the question, is this a random scatter of points, or is there a dependence between these two variables? So that is the point. That is the question we're asking when we are finding the correlation of a set of data. And usually we do that by finding a correlation coefficient, like a factor, correlation factor. So you can see those are shown here for each of these plots, and we'll be learning how to calculate that factor in this class today. And then how to interpret that calculation. Okay. So the way that we determine if these variables are correlated or not is by finding this quantity called the covariance. So there's a whole lot of steps to get to the covariance. And this is the first step here. So first of all, we have to have some measured values of x and y. We have to have a whole bunch of data points, x sub I values, y sub I values. Maybe they correspond, maybe they don't, but we have the same number of each. We have n x sub I values, we have y x sub I, y sub I values. Sorry. And we're going to go ahead and assume that, or somehow we know that the uncertainties in x and y are small and random. So somehow we have verified that already. And then it's okay to approximate each x sub I value with the average of the x sub I values. And then it's also okay to approximate each y sub I value with the average y sub I values. Okay, so with these assumptions, we can proceed. And let's say we take n measurements of x sub I and y sub I pairs. These are measurements. And we're going to calculate some q sub I value with our pairs of x sub I and y sub I. So I'm trying to use the same color scheme as before, where x and y are measured quantities and q is like a calculated something with the x and y measured quantities. So we can find the mean of the x values, x bar. We can find the mean of the y values, y bar, and find a corresponding q bar value. That is just q with x bar substituted for x and y bar substituted for y. So we're finding kind of an average q by substituting the average x and average y values into this function q, whatever it is. We didn't state the function q yet. It's just some function of x and y. Okay, and then we can find the standard deviation, sigma sub q, written in this format. Sigma sub q squared is going to be 1 over n times the sum of the individual q values, the difference of the individual q values and the average q value squared. Okay, so nothing too crazy here. We're not doing any fitting or anything yet. We're just thinking about average values. We don't have a function to fit, so we can't really fit anything. We're just quantifying our standard deviation with our set of x sub I and y sub I pairs. Okay, so now we're going to take our, and again, we're trying to get to covariance eventually. So a couple more slides, we will be there. We're going to take a Taylor series expansion of this q of x and y, this average value of q. And we're going to expand it around the average value of x and average value of y. And just so you remember, here's the function for the Taylor expansion. And remember that Taylor expansions can be used to approximate a function if the differences between all the values and the point about which we expanded are small, as they are here. That was already one of our assumptions. So we're going to apply this function or apply a Taylor series expansion to this function, meaning we're going to find Q sub I by treating F, or by considering our function F to be Q. And we're only going to take these first two terms. We are not going to worry about second order terms or higher order than second order terms. We know those get really small anyway. The higher the order term, the smaller the value, and so it's not going to matter anyway. It's going to be negligible. So we're going to take the first two terms and consider those for our Taylor expansion of Q. And now we're going to take this new version of what Q sub I is and combine that with our definition from the previous slide of the standard deviation squared. So we're literally taking this expression, this kind of simplified version of Q, because we Taylor expanded it, so it's like a simplified but still pretty correct version of Q sub I, and we're going to substitute that here for Q sub I. So we literally substitute it for Q sub I here into the definition of the standard deviation. Okay, and then notice that Q of X bar Y bar is here in the front, and then minus Q bar is here in the back of that sum. And Q of X bar Y bar is the same thing as Q bar. That's what we said Q bar was here. Okay, so that means this term and this term add to 0. So we end up with a simplified version here of that standard deviation squared for our quantity Q bar. Okay, questions so far? Anybody? Okay, I'm going to go back a slide again. So remember, we're finding the covariance. We are going to define the covariance soon. We're getting to that point where we can see it in the math and then define it. So we're considering this value, the standard deviation for our Q sub I values, and we have simplified Q sub I with a Taylor expansion and substituted that into that standard deviation. So simplifying that standard deviation expression, we get this, and I'm continuing that expression at the top here of the next slide. And now there's just math. So notice this is a sum of terms that is squared. So we're going to FOIL the two parts of the product. We're going to take this and multiply it by itself. And so that's what we're seeing in this next line. And I've taken away the I equals 1 and n here just to reduce text. So that's still there, it's just implied. So when we FOIL out this product, this square, we get this term with x's, this term with y's, and then a combination of the two. Still in the form of a sum from I equals 1 to n. Okay, then we can take this part of the sum. Okay, so the sum of x sub I minus x bar quantity squared is the definition of the standard, or with 1 over n, is the definition of the standard deviation squared of the x sub I values from like way back. And then same thing where we have 1 over n, the sum of y sub I minus y bar, that quantity squared. That's equal to the standard deviation squared for the y sub I values. So we just took those terms, and this does not have an x sub I in it, so we can pull it out of the sum. Also here, this does not have a y sub I in it, so we can pull it out of the sum. So we just rewrote these first two terms here as the derivative squared times the standard deviation squared. Derivative squared times standard deviation squared. And then we're still left with 1 over n times 2 times the derivative with respect to x, times the derivative with respect to y, times the sum of the quantities with x sub I and y sub I left over here. So not a ton of crazy math here. It looks like a lot, but really not much. Now we can finally define the covariance. This quantity that's going to help us determine whether or not variables that we have measured are related to each other. Are they dependent on each other? So we take basically this term, this last term, and the 1 over n in front, and that is what we define as the covariance. So sigma sub xy is the covariance, and it's 1 over the number of points times the sum of the residuals squared, basically, or residuals multiplied with each other. So for each x sub I point, I subtract the mean of the x sub i's. For each y sub I point, I subtract the mean of the y sub i's. I multiply those two quantities together for each I value, then I add all those up and divide by n. So that is my covariance. And now my standard deviation is going to be this simplified expression. Okay, questions? Okay. Why do I care about this covariance? Sigma sub xy quantity. Well, if n is really large, then it helps me figure out if these values are correlated or not. So if n is very large and sigma goes to 0, so basically the difference between the mean and the x sub I value times the difference between the mean and the y sub I value, if I add all those up and that goes to 0 as n gets bigger, then those two quantities, x and y, are independent of each other. They are not correlated with each other. If n is very, very large and this sigma sub xy quantity does not go to 0, if the limit is some non-zero value, then that would indicate my two quantities x and y are dependent on each other. They are correlated with each other. So if you have a significant non-zero covariance for large n, you have correlated variables. So how significant, how correlated, that is what we want to understand the meaning of and be able to quantify. For the most part, we're going to be thinking of linear correlation in our class. Beyond, there may be other kinds of correlation, like maybe two variables are quadratically dependent on each other or logarithmically we're going to think about linear, especially for right now. So if we look back at our examples, we see that this looks like it's pretty linearly correlated. Looks like those are linear. There's a linear dependence here. But if I look up in this plot, I have no idea. That could be linear, it could be quadratic, I don't know. Exponential. Looks like just a bunch of random points. So I can quantify that correlation by finding this covariance and then relating that to a probability of correlation or non-correlation. So for a linear case, a special case, the linear case, we can define a linear correlation coefficient R using this inequality. The standard deviation of the x values times the standard deviation of the y values is always, the product of those is always going to be bigger than or equal to this covariance, sigma sub xy. And so we can use this inequality to help us also interpret this linear correlation coefficient R. So anyway, R is defined as sigma sub xy divided by sigma sub x, sigma sub y. It is equal to the covariance divided by the standard deviation in x values divided by the standard deviation in the y values. So we substitute that covariance definition in the numerator here that we got from this term of our standard deviation in Q. And then we divide by the standard deviation in the x values and the standard deviation in the y values. And we have to take a square root because, you know, the definition is the standard deviation squared. So it is always going to be the case, since we know this inequality is true, it is always going to be the case that R is smaller than 1. R is the absolute value of R is smaller than 1. You can have negative R values, and that's when you have a negative correlation. It's still a correlation. You just want to basically, whenever you find this R value, you want to take the absolute value of it to interpret R. Okay, let's see an example or a little bit more information here. For this linear correlation coefficient, let's think about the equation for the straight line that supposedly would be describing that correlation for this linear relationship. If we find the y sub I minus y mean quantity, we're going to substitute a plus b times x sub I here for y sub I, and we're going to substitute a plus b x mean for the y mean value. And this can be simplified. The a's are going to subtract out, and you get just b times x sub I minus x mean for this quantity y sub I minus y mean. So we can take this R expression and simplify it and show that if we apply this meaning, that we're going to get plus and minus 1 as the best case scenario for correlation. The closer R is to 1, where this this quotient would be b over b, then the better the fit is to a straight line. If this is closer to minus 1, it's still an indicator that you have a very incredibly straight line, a very good correlation between your data and linearity. So the closer the value R is to 1, the more linearly correlated your values are, the more likely they are to have a linear dependence on each other. Okay, so let's look at an actual example with n equals 10. So we have 10 data points for this example. We are asking the question, are the exam scores for the different students correlated to the homework scores? Is there a correlation there? Are those dependent on each other? If the homework scores go up, does that mean the exam scores go up? That's the same question. Are they dependent or not? So here's some data. We're going to let homework equal X and exam equal Y. And we're going to calculate this covariance for these data. Okay, so here is my version of that on Excel. So here I have like the labels across the bottom. We have the student number column here. We have the homework score for that student, and we have the exam score for that student. And we want to know, are these correlated or not? So we're going to calculate the linear correlation coefficient R for homework scores and exam scores. So we're finding the covariance, putting that in the numerator, dividing by the product of the standard deviation for X and standard deviation for Y. So in this column here, I am finding the X sub I value minus the X average value. So X is the homework scores, and then the average homework score is down here, 57.4. So I'm subtracting the X value minus 57.4 and putting that here. And then I found the average exam score, 77.1, the average Y value, and I'm taking the Y sub I values and subtracting the average exam score for this column here. Okay, so finding X sub I minus X and Y sub I minus Y for each I. Okay, and then I'm going to take this quantity X sub I minus X average times Y sub I minus Y average and put that in this column. So that's like the numerator, but not added up yet. And then I'm going to take X sub I minus X and square it. And Y sub I minus Y and square it. And then I'm going to take all those values and sum them up and calculate my final R, which I do here. And I got 0.780725 for R. Okay, so what do we do with this R value? Well, we take that to a table. Table C from the back of your book. I think it's in the back. I am finding what page this table is on. Maybe not. I will let you know what page this table is on. But this is from your book. And what we have here is, depending on n, depending on what our n value is, we're going to have different probabilities of correlation or not. So in our case, n was 10. We have 10 data points. And for n equals 10, we calculated R to be 0.780725. So we go down here to n equals 10, and we go over to where R was closest to 0.78. So we'll round up to 8. Our R value is 8, and our n value is 10. So that gives us a percentage probability of 0.5. And the way that we interpret this 0.5 number is the following. There's a 0.5% chance that the homework score, the X values, and the Y values, the exam scores, are not correlated, which means there's a 99.5% chance that they are correlated. And the higher the N, the better we would know. That's pretty definitive. It looks like they are correlated in this case, which we would kind of also expect from homework scores and exam scores. Okay, any questions about the example or interpreting? All right. In that case, it is breakout room time. And I will be sending you a PDF file of a problem to work on. Just
Dr. Hester?
Yeah.
I just have a quick question. On the exam or homework, do we have to show our work, or can we just use like Excel for calculating that?
For this upcoming homework with covariance and correlation, you mean?
Yeah. Would we have to show all the steps?
You don't have to show all the steps, but if you make a mistake, I can give you more partial credit if you show the steps.
Okay, that makes sense.
Okay. So it's okay to include a spreadsheet like that. You know, that's okay if you don't want to show it like by hand, whatever. Either way is fine. Okay, sending file. In just one moment here. Okay, here it comes. There we go. Should be able to access that, and then I'm going to open up breakout rooms momentarily. Okay, I think we're mostly back. Did anybody get a final result yet? No? I know it wasn't a lot of time.
Yeah, we got an R value of 0.935.
Okay. And then how did you interpret that?
Oh, what was that?
And so how do you interpret that R value?
Well, on the table, it looks like that means there's about a 3.7% chance that the numbers are not correlated. And yeah, that's as far as we got.
Okay. So what can you conclude about, say what, Allie?
I found it means there's a 96.3% chance that it does correlate.
That's right, I think. I need to check my math, and we've run out of time. But it looks like we have an agreement on numbers, and we need to make sure we're interpreting them correctly. So we'll revisit this next time we meet in person and talk about this some more. And you know, think about if that was your expected result or not. Okay, so I'll see y'all next week. Have a great rest of your week and have fun with the recorded lectures on Thursday.
Can I ask real quick what you
Yeah.
got for sigma xy?
Sorry, I didn't hear you, Tristan.
What number did you get for sigma xy?
I got, for sigma xy. I didn't calculate that separately.
Oh,
I just calculated R.
all right. I'll go back through it and see if I get the same R value.
Okay.
Thank you.
Have a
Sure.
great day.
Thank you. Y'all have a great day too.
Thank you. Have a good week.
Bye, you too.